All right. What good is this? Here's a problem. Might be on your SAT test. Here are three objects. Let's call them masses. At the center, everything's static here. Three masses are arranged on the vertices of an equilateral triangle. At the center, I put a mass. What is the force exerted on the mass at the center by the three masses on the outside? Who said 0? Why?
Because they all cancel out.
And that's what you find by doing the calculation, or how do you know that? Okay. You could do the calculation. And I've taught physics many times, places like Caltech and so forth. And what happens is the students start adding this vector up, that vector, and that vector. And they usually will make a minus sign because it's kind of a tedious calculation error, minus sign error. And they'll get a result like that. And so their homework gets turned in, and I say, it's not right. Fortunately, you would have gotten it right. Why is this answer wrong? Well, the answer is wrong because this system has the symmetry of our equilateral triangle. In particular, I can do a reflection about axis 1. Remember good old axis 1? I just draw axis 1 and I reflect it. I'll get the same physical system back. But my answer has reflected from this into this. Remember, every point gets reflected into an equivalent point on the right side. And so that answer is different than that answer for the same system. You can't have two answers for one system. So that answer is wrong. So telling the student this, they'll go back and redo, oh, I found my minus sign error, and I get this answer. But now, that's consistent with reflection about 1. But the symmetry is bigger than that. It also involves the rotation through 120. And so if I rotate through 120 degrees, that goes into that. Has to be, can't be both. So this component of the vector is ruled out. And once we've ruled out that component and that component, we've proven the answer is 0. We didn't have to calculate anything. So symmetry is that powerful. Now suppose, I was easy on you. I asked for the gravity case. Suppose these are 3 nucleons inside of a nucleus, lithium or something, lithium-3. And that's a pion sitting at the center of the system. What's the force on it now? By the way, there are no spins or any other degrees of freedom. Everything's just as you see it. What's the force on a pi meson sitting at the center of 3 nucleons, 3 neutrons? That's 3 protons, whatever. What's the force? You gave me the answer before. Still 0. What if these are 3 black holes and that's a spaceship caught in a horrible region of space? 3 monstrous black holes. It's not Newtonian gravity, it's general relativity. You're almost at the horizons of these 3 black holes. What's the force at the center? 0. Symmetry wins. It's more powerful because it underlies all the laws of nature. So you can already solve problems in general relativity. Quantum mechanics, you can solve these problems because of symmetry. Now you got to be careful. If this thing had a spin like that, and that one had a spin in a different direction and so forth, then the symmetry would be broken. You might not, or maybe this is a snapshot at one time instant of 3 things that happen to actually be moving that just happened to be at that position, that configuration at that time. But that's not a symmetrical situation because they actually have velocity vectors. Then it wouldn't work. But in the cases, the special cases where you have symmetries, it works. Now here's an astonishing fact. I don't know if I actually do it here, but I'll just tell you the answer if we go to the next one. All right, so the force is 0 by symmetry. We said these are 3 masses, and we put a mass at the center, and we did gravity. Okay? What happens if I push this mass a little bit away from the center? What happens? If I push it that way, to the top, upward direction, what happens? Well, now these 2 things are closer, so the force of attraction between them is greater. And the force of attraction here is weaker. And we know at the center, by symmetry, the answer is supposed to be perfect balance, 0. So therefore, this system will start to run away. And if you think about it, if you push it this way, it'll also run away. And that means it'll run away in almost any direction. If somebody sneezes, you have this situation of three masses with one at the center, and somebody sneezes, tiny perturbation, the system is unstable. All static gravitational systems are unstable. You can find equilibrium configurations like this, but they're not stable. Now, let's use Ben Franklin, who invented the concept of electric charge. Suppose these are all positive charges. Now let's put a positive charge at the center. This is what happens in a molecule with the electrons orbiting at large distances, and the three nuclei are all positively charged. The nuclei feel each other, so plus, 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 and plus at the center. This would be like a CH3 molecule. Is that methane? It's not quite methane. CH3 radical. Now what happens? Same argument. Why doesn't the system collapse? Why is CH3 stable? Because now, if I push the carbon close to that hydrogen, the force of repulsion pushes it back. Force of repulsion pushes it back. So now what happens is the thing is actually stable. And it'll sort of oscillate around the center, but it'll always get pushed back. If you don't have repulsive, this is sort of weird, but if you don't have repulsive forces, you can't have a stable world. If all forces were attractive, the world would always collapse. It's the repulsive interactions that maintain stability and allow chemistry to exist.